Thank you for the introduction, and thank you for coming. So, as many of you probably know, that TLS, transport layer security, is probably the most important security protocol or cryptographic protocol that we use. Pardon?
Closer to the mic.
Closer to the mic, okay. Good. Okay, so as you probably all know, that transport layer security is the most important cryptographic protocol. So in the recent years, we saw many attacks on this protocol, like Crime, Beast, Lucky 13, Heartbleed, Early CCS, and so on. And so what is maybe forgotten is the attack, Bleichenbacher's attack. So this attack was issued 20 years ago, and it was applied to RSA PKCS 1.5 encryption scheme in SSL TLS. So it allowed an attacker to decrypt SSL TLS traffic. And many implementations, because it was very serious, many implementations and also the TLS specifications applied fixes. And everybody would probably think that now we are secure, but of course this is not the case, because I would otherwise not be here. So I am presenting you a return of Bleichenbacher's Oracle threat, and this is a very serious attack because, as you know, probably it has a logo and his attack name and so on. Okay. So today I'm going to talk about Bleichenbacher's attack, how it works, then how we started our research and how we performed our attacks on Facebook, how we performed our TLS scans, and how we found new vulnerabilities in different products. And then I'm going to talk about responsible disclosure, how we could identify several vendors, and so on and so on. So let's start with the Bleichenbacher's attack. So on a very, very high level, TLS protocol is divided into two phases. In the first phase, the TLS handshake, the two parties, client and server, have to negotiate algorithms, TLS version, extensions, and so on, and they perform a key exchange. There are three types of key exchanges. So RSA key exchange, Diffie-Hellman key exchange, and Diffie-Hellman ephemeral key exchange. And afterwards, after they exchange the keys, they can proceed with the encrypted and authenticated data transport. So for this talk, it is important the RSA TLS key exchange. So how does it work on a very high level? So imagine we have a client who wants to communicate with a TLS server. So first what he does is he sends a client hello message. In this client hello message he says something like, hey, I want to communicate with you with this TLS version, cipher suites, extensions, and so on. The server responds with a server hello message with the certificate. Certificate contains the public key of the server and a server hello done message. Afterwards, the client sends, so the client has now the public key of the server, so it can encrypt something like RSA pre-master secret. This pre-master secret is used to derive all the secrets in the TLS protocol. So this pre-master secret is encrypted with the public key of the server and sent to the server. Afterwards, the client can send chain cipherspec and finish messages which authenticate the client. The server accepts the client key exchange message, decrypts the pre-master secret, and then can authenticate itself with the finished message. Okay, for the next part of my talk, the client key exchange message is of crucial importance. So this client key exchange message contains an RSA encrypted pre-master secret. And this pre-master secret is encrypted using RSA PKCS 1 version 1.5. So in general, this padding scheme is used to pad and encrypt the secrets. So in order to pad it to the specific RSA key length and to add some randomization to the message. So to give you an example how it is used in TLS 1.2, the first 2 bytes of the encrypted pre-master secret contain 0002. This is signalizes or this shows that it is encryption block type. Then there is a non-zero padding byte scheme. which is terminated with a 00 delimiter, and then there is TLS 1.2 version, which is indicated with version byte 0303. And at the end, we have the pre-master secret. So this is a fixed structure of RSA PKCS 1.5 padding scheme, and which was exploited in the Bleichenbacher attack. So in 1998, so 20 years ago, Daniel Bleichenbacher showed an adaptive chosen ciphertext attack. And this ciphertext attack, chosen ciphertext attack, exploits a strict validation in RSA PKCS 1.5 messages. I will not go into the cryptographic details, but show you a very, very high-level overview of the attack. So imagine we have a client who wants to communicate with the server, sends a ciphertext to the server. And we have an attacker who observes the communication, eavesdrops the ciphertext, and somehow modifies it cryptographically and sends the modified ciphertext to the server. And the client misuses, or the attacker misuses the server as an oracle. So because the server, what he does, it decrypts the message and validates whether it starts with 0002 or not. And depending on the validity of this message, of the decrypted message, the server responds somehow with valid or invalid. And afterwards, the attacker learns something, some partial information about the message, and he proceeds with further messages with the next ciphertext. He learns further bits with the response of the server, and so on, until he can decrypt the whole message. So as I already mentioned, I'm not going into details. There's some math needed behind the paper, behind the attack. So if you want to talk about the attack, just approach me during the coffee break. So, and what maybe you need to know, or what is interesting, is that the attack is also called the million message attack. And because the attacker needs to perform or to issue about million messages to the server. But in the real world, the performance of this attack varies a lot. So in some cases, you can issue just a few thousands of messages. In some cases, you need to issue millions of queries. It depends, strongly depends on the strictness of the oracle. I'm not going into detail here. So how can we create Bleichenbacher's oracle in TLS implementation? So how does it apply? So imagine we have the attacker who wants to decrypt the message, and how can we apply the modified ciphertext in the TLS handshake? So he again sends the client hello message, receives the certificate and server hello messages, and afterwards in the client key exchange message, which contains the ciphertext, he inserts the modified ciphertext, which contains the padded the RSA PKCS 1.5 padded pre-master secret. Afterwards, the server attempts to decrypt the message, and depending on the ciphertext validity, depending on whether the message starts with 0002 or not, then it sends maybe decrypt error or bad record MAC alert or something different. And this way, the attacker is able to distinguish valid or invalid messages. So this handshake can then be performed several times, and the attacker can decrypt the original connection. Okay, so what is the countermeasure that was applied in the TLS specification? The countermeasure is, in theory, very simple. So what the attacker needs to do is, what the server needs to do is to always respond with the same alert message, so that the attacker cannot distinguish valid from invalid messages. And if this is implemented correctly, if the attacker can distinguish valid from invalid messages using alerts or using other side channels, then the attacker has no oracle and he cannot perform Bleichenbacher's attack. So in the next minutes, you just need to consider that we have this Bleichenbacher's attack, and if the attacker can distinguish valid from invalid ciphertexts, valid from invalid messages, then he can apply Bleichenbacher's attack. Okay, so how did the research start, or how did we start? So about 1 year ago, Hanno approached me and said that he performed some initial scans of several hosts, and he found a weird behavior of the Facebook server. And he pointed me out to that the server, instead of responding with general alert messages, it responds with, depending on the client key exchange message, the server responds with illegal parameter alert or bad record MAC alert. We are analyzing it, and we found out, okay, it's really a problem, and we asked ourselves, so is it exploitable? So in order to, and we wanted to prove it somehow. So typically in Bleichenbacher's attack, you decrypt some messages and you decrypt some handshake that was used. But we had an idea, so it would be funny to sign a message with Facebook's private key. Because what many people do not know is that in general, Bleichenbacher's attack can be used also for signing messages. So it is able, the attack allows you to decrypt messages or to sign messages, so to perform any private key operation if the server is vulnerable to it. So there are millions of queries needed. We asked ourselves, would Facebook block us, or is it even feasible to do this? And after several attempts, we were really surprised that it works, and we were able to sign a message. We had Facebook with Bleichenbacher Oracle and with our initials. And if you want to prove it, then we have a script on our webpage, which consists of the signature, and it downloads the certificate from Certificate Transparency and validates that this message is really signed with Facebook's private key. Okay, so we reported it, of course, to Facebook. We got some bug bounties, which was nice. And then Hanno talked about it with some guys, so with Craig, and Craig had an idea, okay, what can we do about it? So we can verify whether Facebook is still vulnerable. And his idea was maybe to play with the TLS handshake, and what he did, he removed the chosen-ciphertext and client finish message. And in case these messages were sent, then the Facebook server always responded with general alert messages. But once these client messages were not there, then the server just responded with a TCP reset in case the client key message was invalid, or the server responded with a timeout. So the server waited for different messages, for further messages. So this was a night side channel. So using this strange behavior, we can again apply Bleichenbacher's attack. So we reported it to Facebook, received bug bounties, and yeah, so this was very interesting. And we asked ourselves, so okay, so Facebook is doing this wrong, so how about other servers? And we asked ourselves, so okay, we can perform some scannings, and we can scan for the vulnerabilities. And so we decided to select careful client key exchange messages with, which could somehow trigger Bleichenbacher's attack and Bleichenbacher's attack behavior. So what we did, so we modified the TLS version. So we inserted an invalid TLS version inside. So instead of 0303, we inserted some invalid bytes there. We inserted wrong padding length. So we moved the padding the zero delimiter to the right or to the left to trick the server, or we decided to send different messages which are not starting with 0002. And we, of course, we also played with our new handshake. So we tested with full and shortened handshake messages, which have chosen-ciphertext messages and finish messages, or which omitted this. Okay, so we scanned only Alexa top 1 million servers because of performance reasons, and we wanted to get the most important servers. And we found out that 2.8% of servers were vulnerable to this attack. So this seems to be not that much, but most of the servers, most of the high-profile servers like PayPal, Apple, eBay, Cisco, and so on were vulnerable to these attacks, which was quite surprising. And from the scientific perspective, it was also very surprising that we saw different behaviors in different combinations. So it was not only one server, only one vendor responsible for this, but there are different vendors. And so what we saw was were different combinations of TCP connection resets or timeouts depending on the TLS protocol flow or TLS messages sent. We send different alert messages in different combinations like illegal parameter, bad record MAC, handshake failure, internal alert, and so on and so on. And what was also interesting from my perspective was that we saw duplicate alert messages. So in some cases, the the implementations attempted to verify or to implement the countermeasure, so they sent only a general alert message like bad record make, always the same. But in case the message was valid or the client key exchange was PKCS1 valid, then it sent only one alert message, and in case it was invalid, then sent two alert messages. Okay, this was kind of nice. So we had many servers which were affected, and we were trying to do some responsible disclosure, and to find out which vendors are affected, who is responsible for these mistakes. And you know from different conferences that there are papers which are handling this responsible disclosure process. In case of, for example, cross-site scripting, this is maybe easier because the developers are familiar with cross-site scripting and with this sort of bugs in HackerOne and so on and so on. But in case of cryptographic bugs or TLS implementation, this is not always that easy. So as we constructed different messages to the servers with the description of the vulnerabilities, so we attempted to approach them, but we also, so we said something like, your server is vulnerable to Bleichenbacher's attack, this is the vulnerability, blah, 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 and what we sometimes got was like, no worries, we use military-grade encryption, and we are safe. So this was, but there were also cases where we found out who was responsible for this. So, for example, but it was also not a solution for us. For example, in the case of Cisco ACA devices, which support only TLS RSA. So as a developer or as a software administrator, you could also switch to Diffie-Hellman and to disable all TLS RSA cipher suites. In case of Cisco, this is not possible, so because they only support TLS RSA. And this Cisco device was vulnerable, and they responded to us, okay, we won't fix it because it's out of support for several years. But we were very considerate about this because there were many websites vulnerable to this attack, and for example, it was like Cisco.com. Okay, I do not know what is the current status of this. Maybe they moved their website to a different product, like. But in the end, we were able, with, so mainly with the help of Hanno and Craig, who have good connections to the developers and to different people behind the servers, we were able to somehow find out who is behind the different implementations. And we found many, many different applications which were vulnerable in different ways. It was interesting. For example, this is the list of our attacks, which is also on our website with the CVEs. And what was, for example, interesting is that F5 products, there were 5 servers having 5 different vulnerabilities, 5 different responses. So I don't know how do they implement their stacks or what do they do with them, but 5 different sorts of vulnerabilities in their TLS stacks. Okay. So we notified them, they fixed this, and so what we did also, in addition to our work, to the responsible disclosures, we were not able to track every vendor. So what we also did as a part of our responsible disclosure, we informed also developers of different test tools like SSL Labs, TLS SH, or TLS Fuzzer, and the problem was maybe that these simple TLS scan applications did not have scans for Bleichenbacher attacks, and we provided them with our scan scripts. And for example, now since I'm in December, SSL Labs contains Bleichenbacher Oracle vulnerability scan on their website. Okay, so this brings us to a conclusion about the future work and in general. So in conclusion, what I propose in the future work, so a few years ago we presented timing attacks on open source implementations. There will be Bleichenbacher side channels here. At the USENIX, maybe it would be nice to take a look at closed source implementations from F5 or other devices. It would be, you would definitely find something. As we could see that using these vulnerabilities, you can do some fingerprinting, and what we also saw in some cases is that some after sending wrong client key exchange messages, the servers were responding with some garbage bytes. So maybe you can perform something like Bleichenbacher's or Hardbake-style memory disclosure. Okay. So in conclusion, we were able to apply the 20-year-old attack, Bleichenbacher's attack, and we showed that it works with different new side channels like timeouts, TCP resets, and so on and so on. And we proved that cryptographic countermeasures are hard to apply even if they are in the TLS specification and even if they are explicitly mentioned there. Okay, so our recommendations are that you disable TLS RSA cipher suites, which are not there in TLS 1.3 because of these reasons, and you should in general disable RSA PKCS 1.5 and switch to elliptic curves or to RSA OP if RSA is needed. Okay, thank you very much.
Few minutes for questions. So I can start with a quick question. So as you mentioned that when you contact the affected vendors, they have different responses. Do you have any thoughts of what fundamentally that make them not motivated or sometimes difficult to fix the problem?
You mean why wasn't it fixed a few years ago before? Or I mean the major problem was that the tools that are provided to TLS developers like TESTCell, SH, or SSL Labs, which is now commonly used tool, does not contain a Bleichenbacher attack scan. So this was well known for example, open source developers like OpenSSL and other developers do not include these fixes, but maybe in a large scale it is necessary that we provide to the developers like useful tools which allow them to test with positive and negative tests so that they can test their implementation and where they are vulnerable.
Hi, you are. Just a question about the remediation rates. Do you do continuous scans still to figure out if notifying the vendors was enough? Because as you pointed out, it may be helpful to tell the administrators if they understand what you're saying.
Yeah, so this is we are not doing that. So we our recent scans that we performed were probably November or December last year, and afterwards we said, okay, we are done. We release our attack paper, and everybody who is vulnerable also can use the newly developed tools or SSL Labs. So now it is much easier to find out where they are vulnerable. So what was interesting is that after our disclosure, there were new implementations popping out. So even like two weeks ago, we found out that there was a new implementation which was found to be vulnerable to some attacks, and it was only because probably one of the test tools found it.
Okay. But maybe it would be interesting to if there's now kind of updated versions of the software running on like these HTTP endpoints or the HTTPS endpoints, to now tell people like your vendor that you bought the hardware from said that this is a problem, so you need to update. So maybe there's still room for improving things with notifications. Yeah,
maybe there would be. So what would be nice is to do something like fingerprinting. So in general, fingerprinting of different TLS server implementations. So instead of contacting the website administrator, you can directly go to the vendor and to tell them, okay, you are vulnerable and you should fix it. Maybe this would speed up the process very much in comparison to go over the website administrator, which was quite boring.
So we might have time for a very quick question.
So my question is about what you were able to get signed using Facebook's private key. Question is what are the implications of that? Because it doesn't seem like you could sign like another server certificate, but maybe I'm missing something.
Okay, it was just a normal leaf certificate. So okay. So the Bleichenbacher attacker is only able to perform RSA private key operations. So you are not able to extract the private key. You are able to sign some messages, but of course this was a leaf certificate, so you are not able to sign further certificates or something with it. So it was not exploitable. It was, yeah.
Okay, thanks.
All right, let's thank the speakers again.
Thank you.